To summarize our notes on parallel database management, parallelism turns out to be really easy in query processing. It's very natural, both pipeline parallelism and partition parallelism. And remember that partition parallelism is our big win. It's the thing that scales up with the size of the data. Pipeline parallelism is nice too, but only scales up with the depth of our query tree. We talked about architectural differences, shared nothing versus shared memory versus shared disk. Shared memory is the easiest to build in software because it's really just a traditional relational database running on a parallel computer. But it requires the costliest hardware. It requires hardware that has a shared memory component, and that doesn't scale up indefinitely. So a big shared memory machine is very expensive, and at some point you can't buy a shared memory machine any bigger than the biggest one around. So it doesn't scale indefinitely, and certainly not to a cloud scale. Shared nothing, by contrast, is the cheapest hardware because it's just commodity hardware on commodity networks. It scales great. It can scale from 1 machine to 10 machines to multiple data centers across the globe. It is harder to implement. You have to do more work to turn something into a parallel system that started out as a single node system. And then shared disk is a middle ground where data access is made to look uniform from this shared disk, but you do have to do communication between RAM if there's partitioning that has to happen across RAM. Shared disk makes updates a bit tricky for things related to concurrency control. We haven't seen this yet, but we will later in this class. Beyond the coarse grain architecture, we also talked about the kind of parallelism we could get for queries. We talked about intra-operator, inter-operator, and even inter-query parallelism. All of these things are possible. Sometimes you use all of them at once. Continuing with our summary, for particularly shared nothing machines, data layout choices are important because the disks can only be accessed by the local machines, and any data that needs to be shuffled has to be shuffled explicitly in a subsequent phase. Data layout choices can minimize the need to shuffle and improve performance substantially for queries where you don't have to look at all of the partitions. We learned that most of the database operations that we've studied can be done to some degree partition parallel. Sorting is parallelizable, hashing is parallelizable by partitions. Even aggregation can be partitioned to a large degree. And of course, once you have sorting and hashing partitions, you can do sort, merge, join, and hash join as we discussed. For complex plans with multiple operators in a tree of operations, we can get pipeline parallelism, although sometimes sorts or hashes will block our pipelines. We can also get inter-operator parallelism via bushy trees if our tree layout is sort of bushy shaped. But it does require often materializing data so that the subtrees that complete can be then consumed at the same time by the output, even though the two subtrees might finish their work at separate times. One thing we didn't talk about much today is transactions. So we will in future be talking about transactions, and parallel systems require new protocols on top of the basic single node transaction protocols that we'll learn first. So these are schemes like distributed deadlock detection and two-phase commit. And we will study these after we study single node transactions. I'll comment in advance of that time that two-phase commit is not a great protocol for the availability of a distributed system or the latency of a distributed system. So if we have a parallel machine like this and one of the nodes goes down, two-phase commit can cause us a lot of problems. A single failure will stall the whole system, but even if it's not a failure, it's just a slowdown, then transaction commit can wait for the slowest worker, a straggler. So we'll talk about that more when we get to two-phase commit.